Now there are two approaches, DMAC approach and DMADV approach. Now DMAC approach is done, which we discuss is define, measure, analyze, improve, and control. It is used for existing processes. The process is already there. We have to improve it. For that, we use DMAC. DMADV, on a simple term, it is used for a new process. Whenever we are trying to develop a new process, we use DMADV approach. So define, measure, analyze, design, and verify. Okay, this is for design purpose. So we will discuss only about DMAC approach over here. Now define. So defining the problem. Here there are many terms. Okay, what we do is there are certain terms. We identify the project CTQ. What is CTQ? It is critical to quality. Okay, we identify that what customer segments have to be targeted. We gather the voice of customer. What is the problems being faced? Exactly, we identify the problem statement. Okay, then translate that voice of customer into critical, the CTQs. Okay, so these are critical to customers. We have to deliver that at the minimum. Customer is satisfied. He's God. He is God. We are getting our business. That's it. Team chartering. Team chartering, it says the project scope, roles, business case, problem, goals and statements, and milestones. So we define who will do it, why will do it, what will do it, when will do it. Got it? What will do it, why will do it, who will do it, when will do it. This is the basic scenario for team chartering. Okay, this is what is done in defining a problem. Then is process mapping. CPOC. CPOC is nothing but supplier, then that is input, then production, then output, then this customer. So this is a CPOC model. So what we say is the complete supply chain is looked into and mapped. Okay, that is process mapping. The problem hai kidhar? Okay, where exactly is the problem? Aapka problem hai kidhar exactly? That you have to identify. For that, process mapping is done. Okay, just to find out the exact process scenario. So this is defining the problem. Okay, we have got a certain problem and we will define. Now, how the satisfaction, customer satisfaction is defined. So how, let us say we get multiple scenarios. Okay, the customer may say that I require this also, I require this also. How we will prioritize what he requires the most and what he requires the least. Okay, it is based on this particular graph. What it says, what is the critical priority? It is functional or satisfactory. Okay, what is the functional or dysfunctional? There is one is there, it gives the happiness to the customer, added advantage. Okay, mobile liya hai aapne, mobile ke andar camera 16 megapixel hai, call nahi karta. Okay, you have taken a mobile. Okay, it is having 16 megapixel camera, front camera, let us say. Okay, it does not call. Would you be happy? It is not, it is not giving the minimum function of calling. What will you use camera for? Camera is a leisure activity. It is a satisfaction. It is an added value, added advantage. Okay, so that's how you decide where to focus first. Okay, so this was a real-time case study in our company. Okay, there was a PCB, printed circuit board. I know electronics engineer very much understand, and I myself am an electronics engineer. So sorry, please, I took this topic. Don't beat me up after this webinar. Okay, so this is like the printed circuit board assembly. For that, this was the problem which was happening in our company, and it was happening multiple number of times. The customer was complaining that okay, we'll stop this business. This PCB is not even meeting the minimum standards, and since it's an automotive company. In automotives, we cannot, take even a single defect. Okay. For that, what we did, first step was gather the VOC. So what we did, inputs we took from all the stakeholders. Stakeholders were basically the internal team and the customers. Okay. Then the major problems came into picture that LED was shorting. So LED was getting short. Okay. So that was the major problem. So and was causing the maximum failures. So customer dissatisfaction was there. So what we did, we declared it as a critical to quality parameter. Okay. Then there was second step. Okay, please note this down. These particular will help you, going through the examples. So whosoever is listening, please note it down. Okay, second step is defining the charter. Now we defined that, okay, business case as to why to do this project. Like I told you, right? What, why, how, when. So we define why we are doing this particular project, define the problem statement. And so what it was here, it was repetition in front of the customer. That is why we are doing this project, right? Then the CFT members were decided, okay, like who. This was the who part. Then we decided that LED short was in X% of the product. So this was specific targeting. What we are going to do, why we are going to do, who is going to do, what we are going to do, and we gave the timelines which said that, okay, when we are going to do. This is how we define a particular project, define a problem segment. Okay. Then we define the project scope. Is it applicable to a single product or processes? Sometimes it happens like, a product is combined to multiple processes. Right? Then if we improve or do any change in a single process, it will impact the other product also. So we found out that also. Like, okay, scope was reducing the problem in model A that included all the necessary processes involved to produce and transport the product. Okay, next was how the improvement expected by the project. So we, to cut it short, we defined that we'll reduce from 20,000 ppm which had gone that time. Okay, not at the customer end, it was internal. Okay, at the customer end, obviously we cannot afford this one. This was IHR initially. For it was a new product, so that's why we decided that first we will go to 1,000 ppm. Now it is a realistic figure, we cannot go for zero defect directly. Okay, we defined 1,000 ppm will be the target. For that, the timeline was defined, CFT was defined. So okay, this was how we defined it. This here we completed. Next point was like process mapping. So we use CPOC model, just like supplier input, process output, customer model, which we told that where is the problem? Supplier is the problem, input is the problem, process is the problem, output or logistics is the problem, or customer itself is having that problem. With that, customer is not satisfied and we are not even dealing with the major requirement of the customer. What is exactly the problem? So that VSM can be used in this case, that I have identified. So VSM we use also. Okay, so VSM is a tool, value stream mapping, which can be used to identify these problems. So the team maps the process without jumping to analysis again. So all the RM supplier list was generated. Okay, input processes were mapped, flip chart, everything. We just noted down everything from supplier till customer. This was the approach. Then measure. We measured, identified the possible causes. Okay, developed the data collection plan, variation, process capability. Now you're seeing it out of 7 QC tool. Now we are collecting the data to measure it. Okay, what is the variation? So there were multiple. We collected the information and data which were used to find the causes. So pie charts were used, bar charts were used. Okay, we tried different vendors for bare PCBs, different lots of bare PCBs, and we found that, okay, what is the scenario? Are they still failing or not? Okay, we just checked it. Work value analysis was used, to find out that process were actually contributing to the customer value. Now, we found out that, okay, whether this particular process is actually contributing to the customer value or actually contributing to customer defect. That is also happened. A non-value-added activity is causing a customer defect. Sometimes it happens like that also. We found some of that problem also here. Anyways, the best and widely used tool Ishikawa or cause-effect diagrams were framed for this problem. This was the problem. LED was short. Okay, let me explain this diagram. So materials, and there is mother nature. We explain it in terms of 6 natures. Okay, mother nature, material, method, man, measurement, machine. So the machine, where the machine is causing the problem, method is causing the problem, metal is causing, what exactly is the root cause of the problem? For that, we developed this particular diagram. So LED was getting short. Now the probable cause will be the temperature higher than 24 degrees Celsius in the method, baking profile. Okay, LED is getting short in the material itself. Solder paste is expired. Okay, there are numerous causes. You will not understand these processes because the processes vary from manufacturer to manufacturer. Don't focus on that. Just focus the basic scenario. Okay, what we did, we found out all the probable causes, and then on the basis of those, we measured, okay, how exactly it is creating the picture. So we did ANOVA analysis, okay, analysis of variance, statistical models we developed. Don't get scared by these terms. Okay, it's just simple mean mode variance. Okay. So we developed all those things. We did sampling. Okay, out of 100 lots, we checked 10. Then we increased the sample size. We did everything. So then random distribution, normal distribution curve is the most widely used. So we use the same over here also. Now there is a very beautiful concept of process capability over here in Lean Six Sigma, which is CP and CPK. Okay, the formula is USL minus LSL by Six Sigma. Now USL is upper specification limit in a control chart and lower specification limit. Out of that, divided by Six Sigma, whatever the value we are getting, it is CP. CPK is towards any side. What is the relevance of these two terms? Like CP can give you a particular figure, like how many terms are within the limits. Now let us say one is into the extreme positive side and one is into the extreme negative side. Okay, they will cancel each other. Before that, CPK is calculated separate out it that minimum for every side is being calculated in this particular scenario to find out that where exactly is the problem. Are they, for example, 10 millimeter is the specification limit. We are getting consistently 11 millimeter. Okay, we are not getting 9. We are not getting 9.9 also. We are getting 11 or 11.2 or something. So we'll focus why it is more than the specification limit. Instead of focusing that it can be less or it can be more, it will be more specified. Okay, that is the basic scenario. And so CPK for the process in this problem is below 1. So customer was clearly not satisfied. The lower the CPK, okay, the worse is the process. It is opposite of that, right? The lower is the CPK, the worse is the process. The better is the CPK, the better is the process. Okay. And again, for Six Sigma, it is like 1.33 is the CPK value. Okay. This is if Six Sigma is followed, 1.33 we get or 2 around we get. It is a perfect process, right? 1.33, sorry, 1.33 is for 3 Sigma, 2 CPK value is for 6 Sigma. That's how we define a particular process. It is good or bad. If it is less than 1, definitely customer is dissatisfied. Then we analyzed. What we do in Analyse, narrow the root cause. So whatever we found out in those, Ishikawa diagram, we narrowed down the root causes by hypothesis testing, t-test, chi-square regression analysis. Here we did the hypothesis testing and regression analysis. Chi-square is done only and only for qualitative measurement. Like, RAM is black or not. RAM is black or white. So black, white, this color and qualitative concept when it comes into picture, we use chi-square test. Okay. When it comes about like the quantitative test, we use hypothesis, t-test and regression analysis. Okay. Then we no need to understand it at this particular phase. Just understand the basics. Okay. Quantify the opportunity, the quantum of benefits from root causes. What exactly, again, the engineering economic analysis which we discussed before, the cost benefit analysis, whether it is really, feasible or we should go ahead with that or not. Then we analyzed the case study and found out that, okay, this LED is getting short, maximum 90% of the cases is because of the suppliers. Okay, by this hypothesis testing, we found out this is the cause. And then quantum of benefits, we found out that, okay, if this particular problem is reduced, like the 1000 ppm, that is our target, right? If we reduce it to that particular target, what will be the cost benefit analysis? So instead of analyzing at this particular stage, we just decided what is the rejection improvement we'll be getting, like how much improvement we'll be getting. For example, nowadays we are getting like 20,000 rejected pieces. In future, we'll be getting only 1,000. So service call will reduce it, all those things, right? So all those things we are looking into. So that's what was the target over there. We analyzed and we found. Then we improved. In this improved, what we do it brainstorming. Generate or select solution. We list down all the solutions. Then we brainstorm or we do criteria matrix. In criteria matrix, we provide a weightage to particular solution. For example, solution 1, solution 2, solution 3, solution 4. Weightage for solution 1 in this particular scenario is 8. Like it will reduce material handling by 10. It will reduce, this rejection of LED shorting by 10. It will reduce by this. So just such how the weights are provided and accordingly a score is calculated. Nominal group technique follows the same thing. Theory of inventive problem solving says when there is no past data, when there is nothing at all, experts' views are taken into picture. So that is inventive problem solving. Solution selecting tools, we have select other tools as well, which are invented by ourselves also. That is where industrial engineering is very flexible. It is a common sense. You can do anything, but in a standardized way. Refined solution. So then we did Poka-yoke. What is Poka-yoke? in every process, there are many fools around there. Okay? So we need to foolproof. There are many fools around there who can do anything. So we have to foolproof the process that even a fool comes over there, it will still be successful. Okay, that's what is a refining the process. Then it's testing the solution. We tested the solution on the pilot planning, and then we verified the results. And then the final and the most important topic is paisa kitna milega, right? Monetary measures kitna hoga. So when we talk about cost benefit analysis, we are investing certain amount, or we are investing certain amount of energy and resources. What will get out of it? Is it worth putting those that amount of energy into that? That's what is the thing. Then there is the results verification. Okay, then in failure mode effect analysis, which I told about, that is a very beautiful tool. What we do it in that is we convert in a particular score is developed, which we'll discuss in next slide. I'll explain it a little, although it is not very relevant at a particular stage, but still I'll explain because the knowledge should be there. And let us say improving case study. So generate, as I said, that we generate a particular solution, then we refine using those methods. So failure mode effect analysis, what we do is risk priority number. If we implement this, what is the risk? Okay, higher the risk priority number, okay, the higher is the problem. The lesser is the risk priority number, the more foolproof it is. That is how it is implemented. Okay, so and also it is otherwise. This problem is critical. How critical it is? In that case, also failure mode effect analysis can be used. Okay, to find out that. So that then we test the solution. Okay, then we justify the solution. We do cost benefit analysis. Then control. No process can sustain unless we have a controlled, documented scenario. For example, you start a exercise routine. Okay? After a certain period of time, you leave it, right? You are not going to gym anymore. You are not going to work out anymore. So is it sustained? No. You'll get back to your previous body shape after a certain period of time. So to sustain that process, we have to ensure that that process is followed continuously, and that with ease, just like we breathe. Okay, for that we maintain the solution in the form of, like, we document it, we develop some charts, we continuously monitor them. So then the process management chart, process documentation is followed. The selection of control chart is there. Okay, then interpreting control charts is there. Then we close the project by documenting everything, providing that these are the standard operating procedure, and we close it. This is how it happens. Okay, so quality of solution into acceptance of solution is the effective solution. Why we said acceptance of solution? Customer is God. Huh? We can do a lot of state-of-art methodology. Customer says, I don't require it. You have lost it. You have to listen to the customer acceptance. If he accepts it, it is effective. So that is what we test over here, and then we sustain. So then there is a process control chart. Here, X bar, R chart, and P chart were enough. Okay, where they are used, X bar chart is nothing but, for example, there are three types of chart: X bar R chart, P chart, and C chart. There are three types of chart. X bar R chart is done to know whether, like, for example, 10 millimeter is the specification limit, and true value, and 11 and 9 are the upper and the lower specification limits. How many times it exceeds the 11, how many times it is below 9, that the number we have to find out. For that, we find out X bar R chart to find out that a particular piece is defective or not. That is X bar R chart. For P chart, we find out that out of a certain lot, how many pieces are defective. Okay. Now for C chart, what we do it in a particular piece which is defective, how many defects it is having. So I'll repeat. X bar R chart is used to find out that a particular object is defective or not. P chart is to find out number of defectives in a lot, and C chart is to find out the number of defects and the defectives. Okay, this is how it is being used. So here we found out that the project was documented, the result and the sustainability were monitored, and possibility of horizontal development were analyzed. And we found out that a similar process would be implemented in a similar plant over there in Uttarakhand. So this is how this methodology worked. We didn't have to repeat this methodology to implement it there. It was just a bread and butter case. Now the most fancy topic. Okay, it is the end of the topic. So, and now why we need a new recipe? Because we lose the taste in the new recipe. So yes, the last recipe is not tasty anymore. So we are going for a new recipe to develop the manufacturing concepts. So we have become white collar workforce, and automation has become a necessity. This has been a comment done by given by Randy Brooks, president of Motion Industry, and it is a very beautiful comment. What type of job you want to do? Okay, what is the target of Industry 4.0? Replacing or empowering humans? So what type of job you want to do? Do you want to do that operator job? No, nobody wants to do that nowadays. That is just a job which machines can do. We want to do the smart job, right? What is the target of Industry 4.0? Replacing or empowering humans? It is just to empower the humans, to make them more skilled. Okay, it is not to replace the humans. No machinery, let me tell you, no matter how intelligent it is, it cannot replace humans. Okay, will we overthrow the existing steps to adopt the new technology? Not at all. Are we exposing our organization by risk by doing so? Not at all. Again, it is all about connectivity, intelligence, and flexible automation. Okay, it is about just imagine you are standing and taking the data. Just example, cycle time. Okay? You put a smartwatch. Okay, the changeover is happening in the process, and you forward to stop. Now you'll have to wait till the next changeover to find out the next time, and still a single reading is not capable to analyze anything. You need a minimum of 30 readings. So would you wait for 30 days or 30 proper time to do that? It is very hectic and it is impossible, next to impossible. Okay. In addition to that, just imagine a situation the machine was running at a speed lower than the average, which you didn't observe. Okay. Now where you are where you had started. You didn't arrive to any solution. You didn't arrive to any data. That data is absurd. You have to discard it and you have to do it again. So to avoid that, the hard part of data collection is done by Industry 4.0. This is the only part which Industry 4.0 does. Okay, to help do the processes efficiently and to collect the data for industrial engineering. I'm talking about only industrial engineering. Okay, that is what it does. So the answer is same. Why do we need computers? To err is human. Okay, we are prone to errors. We will do errors. We cannot be perfect. And another thing is garbage in, garbage out. Now the data we are putting it, if it is absurd, no matter how high quality computers we are putting it, we get the garbage out only. We'll get the difficult, the wrong decision only. Okay, disastrous decisions. So instead of that, we have to have a reliable data. That is the target. So we will always are in a super dilemma and take delayed decisions. This is the human tendency. We always say this will happen. No, if this happens, this will happen. If this happens, this will happen. We should be clear, and that clarity will happen only when the data is reliable. Usual maintenance team is much like in the movie Police. This is very much true. I have experienced too much. कभी time पे नहीं पहुंचता. Like सब कुछ हो गया अब आ रहे. Okay, so to avoid that, okay, we should know that when a particular machine is going to fail, so that beforehand only we'll able to analyze. We'll take some actions. Okay, that is how the usual maintenance team should work, and it will work with the help of Industry 4.0. So why do the monotonous work when we can do the smart creative part? That is the basic principle. So what happens to the traditional concepts? Basically, just I'm reiterating, data is collected using Industry 4.0. It tells us what happened, why it happened, what can happen. On the basis of that model, we analyze, if this can happen on this particular data, what are the variations which are going to be coming in the future? Let us put that also in this model. We put in that model, then the decision support is given, then that decision automation is given. Once we decide on a particular scenario, this has to be decided, it learns automatically. It gives some machine learning and artificial intelligence works into that. And then the decision is taken. So the system gives us a particular decision, but ultimately we are the deciders. Let us say there are some things which have been left out with, but we have to look into only some things. We don't have to look into those hard part which you used to do before. And let me tell you, no human mind is so much perfect to analyze everything at one go. we can just focus on one thing at one go. That is why this helps. Okay, then action is taken. So what happens to the traditional operation concept is the concepts are the base and IoT is the tool to develop the world-class facility on that base. Again, the base always remains the same. Smart manufacturing just eases the collection, analysis of data. Decision making shall still need the traditional operation concept, which you just learned, the Lean Six Sigma, Lean manufacturing, which you will be learning soon. Value stream mapping, Kaizen, TPM, inventory management, project management. These all are the concepts which will still be enacted. And there are many more concepts. So IoT will just work on that. In a nutshell, IoT is the logical extension of the operations concept. Now, the most important thing. Why we are doing that? Why we have spent so much of time over there listening to this industrial engineering and all. Let us come to the most interesting point. Yes, you opportunities. Okay, so irrespective of any transformation in technology or industry themselves, there shall always be a scope of improvement. This you very well agree, right? So yes, there will be a need of industrial engineers. Plus, let me tell you, industrial engineers can do anything. They can do wonders in the world. Okay, electronics, they have restriction to complete, electronics things. Electrical, they have restriction to the power transmission line. Mechanicals, core mechanicals without industrial engineering, although mechanical industry engineers normally know industrial engineering. But let us say mechanical industry, imagine mechanical industry without industrial engineering. They will design without even thinking whether it is manufactured or not, whether it is manufacturable or not. Again, the use of industrial engineering will come into. We are the gold. We are the diamonds, in fact. Okay. So every manufacturing company had higher requirements of industrial engineering. This is true. But yes, consulting companies also require industrial engineers to let them develop that system for the service industries. That's how you have, the opportunities in both manufacturing as well as service industry. Now, as per Princeton review, most of the industrial engineers reach the higher management position within 10 years from the starting of their careers. The example is in front of you, by the way. Okay, I raised really fast. I rose up really fast. And if you really want to experience, just ask any industrial engineer how they will say they are happy. Actually, they are happy. Obviously 90% or 10% are always there. They will say no, nothing, we are doing the same thing and all that. Don't follow them. That follow the positive vibes you're getting from that. The people get successful, and success does not come for free. Okay, success is always logical. Success is always, it comes at a cost, and you should enjoy the cost. Okay, don't pay the price, enjoy the price. As per the McKinsey reports, reskilling shall be required in the future, and the job shall be for data scientists who have the knowledge of both industrial engineering as well as IT tools like R, Python, MATLAB, etc. That is why I reiterated on both the concepts, the smart manufacturing as well as those concepts of industrial engineering. If you know both, you are the masters of this particular industry. Not even a single company can deny you if you know these things, if you're skilled enough. Okay, and if you start working in any industry, okay, nobody can deny. Okay, this is how. Then, as per the truity, the jobs for industrial engineering are going to rise by 8% by 2028. Relief? Okay, obviously they will increase. Actually, other engineers, I'm not sure, but this engineering has a lot of scope. Average base salary for industrial engineering is 4 lakh, 4 lakh 5,366 per year. This is just, averaged out. You might get a bit lesser, you might get a bit more also, but I'll reiterate, for the start, don't look at your salary. To the start, look at your learning. You will rise very fast. I'm telling you. Let me assure you again. So, sir, these are some of the references. I will share my presentation with the, the Skill-Lync team also, and you can anytime go through these, links to just to get the gist of how, industrial engineering is required in the market and how they are performing, industrial engineers are performing in the market. Okay, and thank you so much.